it's been about 2 years since I've given a presentation to a live audience, so thank you very much for coming. It's great to see ECOC managing to put a live trade show despite all the challenges. So we've been covering progress of silicon photonics for almost a decade now. And in this presentation, I would like to kind of ask a question, what is really driving the adoption of this technology? Is it the technology itself, or is it the business strategies of companies behind it? So if we go back and look at how silicon photonics started, I think the big bang for market adoption of this technology was Cisco's acquisition of Lightwire. It was a startup with no products, but they patented technologies. They demonstrated that silicon modulators indeed work very well. They're particularly useful for PAM4 modulation. And just because of that, Cisco paid more than $250 million for acquiring Lightwire. So in my mind, it was a big bang for silicon photonics in the market. If you look at the researchers, they've been studying silicon photonics for decades before that. Even companies like Intel were investing in it since 1990s. But I think Cisco really put this technology on the map and generated a lot of excitement in the industry. So several of Cisco competitors followed with similar acquisitions, maybe on a smaller scale, often just following the lead of Cisco, acquiring technology just in case. A lot of analysts were excited about how soon silicon photonics is going to get adopted. One of the financial analysts published a very good report outlining all the advantages of silicon photonics and came up with a really bold prediction that in 3 years, everything is going to be made of silicon photonics. Finisar is going to be out of business. Of course, Finisar was making transceivers based on gallium arsenide and indium phosphide. Well, the report was great. The only problem was that, the timeline of adoption of silicon photonics was a bit exaggerated. So I think, this was early after the Big Bang. The temperatures are very hot. So there's so much excitement. There's no atoms or molecules or any intelligent life formed yet. So we actually waited a couple of years before starting to forecast adoption of silicon photonics. And I'll show you our forecasts in the next few slides. But I guess I'll start by pointing out that, Finisar is still very much in business. In fact, they had an excellent, almost a decade after, silicon photonics was supposedly taking them out of business. So Finisar is still remaining number one supplier of optical transceivers as part of II-VI. InnoLight, of course, made a lot of progress over the last decade, so they're very close, number two at this point. But to be fair to silicon photonics, we do see new entrants on the top 10 list of optical transceiver manufacturers who really took advantage of silicon photonics technology and entered the transceiver market quite aggressively in some cases. I think Intel was probably the most aggressive entrant. Cisco entered this market by acquiring not only Lightwire, but then Luxtera and more recently Acacia. Huawei also made a small acquisition of a startup company based in the UK. However, most of their efforts were really internal development of silicon photonics, and they are shipping quite a lot of products based on this technology. So we rank them number 3 on the list. So if you look at the reasons why silicon photonics technology is important for companies like Cisco or Huawei, I think this slide illustrates the point fairly clearly. And, Cisco makes no secret about their strategy. So if you look at the market for data center switches or optical transport equipment, optics is becoming the dominant contributor to the cost of those products. It's also becoming the main barrier for the speed of innovation in switching and optical transport market. So by acquiring silicon photonics technology, Cisco was able to enter the market for manufacturing optics with fairly limited investments. Of course, they spent billions on acquiring companies, but the advantage of silicon photonics is that it could rely on standard CMOS foundries. So they didn't have to go through years and decades of fine-tuning indium phosphide processing in order to enter this market. And I think Huawei used a similar strategy, even so they're more diversified. So Huawei also has significant investments in indium phosphide. And I'll point out later in my presentations that it's not really just silicon photonics itself. It's really a combination of technologies that is important for many of the product's designs. If you look at the reasons behind Intel's interest in this technology or Broadcom's interest in this technology, it has to do more with the design of the next generation switches. And Broadcom publicly announced their plans for introducing data center switching ASICs with co-packaged optics by the end of 2022, so a little more than a year from now. And that will be just the first step in integration of optical engines with IC functionality. So starting with switching ASICs, but we're seeing a lot more work actually going in the supercomputing community, designing optical connectivity for co-packaging with GPUs, CPUs, TPUs, and I think eventually we're going to see optics interconnecting chips that now go within a single package. I think as the power consumption becomes a barrier for advancing electronics, we're probably going to see more demand for optical connectivity for very short distances. And I think all these trends we're going to see unfolding over the next decade. Again, when we do our forecast, we're a bit more pragmatic in terms of how long it will take for new technologies to penetrate the market. But our experience that forecasting the market and staying on a more conservative side is actually the right approach to providing good reference point for the industry and helping companies to plan their business. So I'll show you a few slides with our forecasts, and I'll start with a forecast that we published 5 years ago, actually a little more than 5 years ago. It was published in January 2016, where we looked at the total market for optical transceivers, and in 2016, only a small fraction of those were made using silicon photonics technology on the transmitter side of the device. So when we talk about silicon photonics-based transceivers, we really look at technologies that are used on the transmitter side of the device. So our forecast was much more conservative than some of our competitors, but if you compare it with the chart on the right, which is the actual market data that we've collected from the market over the last 5 years, it was fairly close to reality. I mean, the accuracy of forecasts deteriorates with time. So it's hard to forecast for 5 years. But for 2-3 years, the forecast was actually fairly accurate. I think the highest share of silicon photonics that we are seeing in 2020 and 2021 is partly due to change in our methodology. Back in 2016, we only looked at transceivers made by manufacturers like Finisar, Innolight, and others. Starting with last year, starting with Cisco's acquisition of Acacia, we started to include transceivers made by companies that manufacture networking equipment. Cisco, Huawei, ZTE. So this jump in the share of the silicon photonics in 2020 has actually is mostly due to change in our forecast methodology. So we included products made by Huawei, ZTE. Acacia was included before as an independent company, but it turns out that Huawei ZTE actually make quite significant number of silicon photonics-based transceivers, mostly for DWDM applications. You can also see that the market didn't grow as fast as we expected. And in fact, if you look at the market in terms of number of units, it's actually exceeded our expectations. But what happened is that prices declined a lot faster than we anticipated. So the growth in terms of sales ended up being a bit slower. And in fact, some of that reduction in the growth rate can be traced back to adoption of silicon photonics. For example, when Intel entered the market for 100 gigabit Ethernet transceivers, they were very aggressive in gaining market share at the expense of lower prices. So in fact, some of those, if you look at 2018, 2019, growth in sales was fairly modest. But growth in terms of number of units was still very strong. So it's an adverse impact of kind of new technology and new competitors entering the market that, they intensify competition, so that limits market growth. So this is another chart that we published more than 5 years ago when we looked at the same market, and you can also see silicon photonics on the top of this chart in dark blue. But we also looked at other technologies and separated them into integrated and what we call discrete devices. So when we talk about discrete devices, these are very simple, directly modulated indium phosphide or gallium arsenide lasers. And we certainly anticipated that demand for more complex devices, starting with products based on electroabsorption modulated lasers, or EMLs, that incorporate two functions into one element or one chip or co-packaged element. So the share of integrated devices was expected to grow. In fact, it grew much faster than we expected. So if you look at the actual market data, the share of discrete components today is only 20% in terms of sales. We were expecting to see about 40%. So the share of integrated optics increased also faster than we expected. Again, with the sales, prices are often make a big difference. So pricing of some of the discrete components sold into fiber to the home market or a wireless front haul market, because a lot of it is deployed in China, prices are very, very aggressive. So that was the main factor why sales of discrete components are only 20% of the market today. So I'm going to switch to showing you data from our more recent report. So this is a forecast that we published in May of this year. And it just looks at the sales of integrated optics. So we're excluding all the discrete components. And you can see that, the growth of the market is very strong if we just look at the integrated products. And we also separate, we quantify integration in terms of scale, starting with simple devices like electroabsorption modulated laser, which we characterize as a 2x integration. So we combine two functions into one optical element. So 4x integration examples are like CWDM4 transceiver, which uses 4 different lasers, also co-packaged one way or the other. And then the strongest growth we see in the category, which we call a large-scale integration. So it's either 8 lasers per array, or it could be more complex integrated circuits used in, for example, coherent DWDM optics. So coherent DWDM optics, that's where Acacia had the most success with their first products dating back to 2015, 2016, when illustrated on the left side of this chart. So they had early success with coherent 100 gig, coherent DCO transceivers. Their latest products are taken integration to the next level. So they not only combine many of the optical functionalities in one chip, but they co-package photonic integrated circuits with a coherent DSP. All of it is made of CMOS. It's made using different processes, but it can be 3D stacked into a tiny little sandwich, if you will, to optimize the performance of the chip. And it's really critical for high-speed integrated circuits. So I think, in addition to market strategies, I have to admit that, yes, silicon photonics does have an advantage when it comes to integration with electronics, particularly when you look at like 3D packaging capabilities. If you look at a broader market, you take, for example, CWDM4 transceiver, it can be made from indium phosphide or silicon photonics. I don't think there is much of a technological difference between the two. In fact, most of the products enter the market based on indium phosphide designs. For example, 400 gig devices, if you look at FR4 or DR4 400 gig transceivers, majority of these sold today are still using indium phosphide technologies. And silicon photonics designs are still behind. Intel is entering this 400 gig market today. But early implementations use kind of legacy technologies, if you will. So the advantages of silicon photonics are not really apparent until we come to the stage where tight integration with electronics is required, whether it's DSPs, coherent DSPs, PAM4 DSPs, or switching ASIC co-packaged with optical engines. So I think over this decade we're going to see more products where silicon photonics really has an advantage. So if we look at our forecast for the next 5 years, we are optimistic that the share of silicon photonics, and this chart just looks at adoption of silicon photonics in the DWDM market. So that's where the complex photonic integrated chips are required, and we expect that many of them will be integrated with coherent DSPs. So the share will increase. However, indium phosphide technologies, demand for indium phosphide will continue to increase. In fact, what we're seeing in the market today, most of the designs for 400ZR DWDM transceivers are based on silicon photonics. But if you look at ZR Plus or other higher performance type of devices, majority of suppliers are using indium phosphide because it does have some advantages in terms of performance. So silicon photonics is going to do well, but indium phosphide is not going away. And there are a lot of work that's going on that technology as well. And as I mentioned, companies like Huawei are well diversified. So they investing into silicon photonics, but continue to invest in indium phosphide. If you look at Ethernet market for silicon photonics devices, this slide dates back to 2012 when Cisco acquired Lightwire. This were the first results that Lightwire showed how silicon photonics-based modulators can be used for PAM4 modulation. And indeed, they work very well because the more complex integration, the better chances are for silicon photonics to compete with other technologies. So that will certainly continue in the Ethernet space. So we're looking at PAM4 to be the primary modulating format for not only 400 gig Ethernet, but also 800 gig, and that's starting to sell, and 1.6 terabit, that's probably 3-4 years away. So PAM4 modulation for the optics is here to stay. And again, integration of PAM4 DSPs or co-packaging PAM4 DSPs with optics will help designers to mitigate impairments issues with handling of high-speed signals. So if we look at the market for Ethernet optics, we're also optimistic on the progress of silicon photonics. So it will become probably the number one technology in the Ethernet market by 2026. But we don't think that gallium arsenide or indium phosphide are going away. I think the deployments of both technologies will continue in the market. Some cloud companies arguing that multimode fiber is not a future-proof technology. But on the other hand, if you look at the VCSEL-based transceivers, they're extremely power efficient. And yes, there are challenges to transmit those signals over long distances, but in many applications, the distances are shrinking. So we see quite a number of large cloud companies still committed to deploying multimode fiber. And the cost of fiber, by the way, is dropping very steeply this year. So deploying more fiber is not going to be such a big cost in the future. Companies like Google that's been using multimode fiber in combination with single mode fiber, they are leaning towards switching more to the single mode fiber in the future. But even with that, they still plan on deploying indium phosphide-based optics. So they have no preference between indium phosphide and silicon photonics. Ultimately, they only care about price and reliability. Reliability is becoming an issue as we go to higher speeds because lasers tend to degrade. And the higher the current, the faster they degrade. So some of the advantages of silicon photonics, I think, come also from higher reliability. Even so, gallium arsenide and indium phosphide experts would argue against it. But if you look at the fundamentals, silicon photonics is, it's a different material. So the silicon photonics modulators are certainly more reliable than, say, directly modulated laser. The counter argument is that because of high losses in silicon photonics integrated circuits, you need a high power indium phosphide laser to pump it. So you're kind of still dependent on the indium phosphide lasers that may ultimately degrade. So that's why when we look at designs for co-packaged optics, many of the designs are based with an assumption that the laser is going to be an external device that can be replaced to mitigate reliability or lack of reliability in those next generation systems. And if you look at the total sales of silicon photonics-based products, the two major markets will be DWDM and Ethernet optics. But the icing on this cake is co-packaged optics, which shown as this pink color. So it's definitely happening. When Broadcom make commitments to the market, they always deliver. So we're confident that co-packaged optics will start penetrating the market. However, when we talk to potential customers for co-packaged optics, they are certainly very cautious about how fast they're going to adopt technology. They are interested, and they will certainly try it out, but we would argue that until it's absolutely necessary to use co-packaged optics, the pluggable optics will continue to dominate as a deployment. So even 5 years from now, when we look at the deployments of co-packaged optics in data centers, for example, if we look at deployments of 800 gig Ethernet optics, we argue that almost 90% of these deployments will be still based on co-packaged solutions. And companies like Google, for example, they're not planning to use co-packaged optics anytime soon. Microsoft, Facebook, Alibaba are certainly more open to at least testing co-packaged technology, but they would like to see this market to become mature. They're very hesitant to jump on solutions manufactured just by one vendor. Even so, this vendor may be Broadcom, but they really don't feel like being locked into just a single supplier that can kind of dominate this market. So they would love to see the whole ecosystem develop around co-packaged optics before they seriously commit to massive deployments of this technology. So full disclosure. So, one of our strategies working with the industry is that we're very honest with our customers. So we admit our mistakes. We tell from the beginnings that future is unpredictable. We always point out on mistakes we made in our forecast, and I started showing our forecast by looking at data we published 5 years ago. So warning again, take market research with a grain of salt. So when we report on adoption of silicon photonics, we have to really simplify the picture. The market reality is much more complex. Some clients come to me and they tell me, I don't even know if our product is based on silicon photonics or not. I mean, we use such a huge variety of technologies. We use indium phosphide, we use micro-optics, we use silicon germanium. Yes, there is silicon photonics too, but we don't know how to classify this product. So the reality is messier. The other point is that silicon photonics is, it's a magic technology, but it's not perfect. And it's limited in their capabilities. So we're going to see that probably the best designs will use a combination of technologies. And indium phosphide, of course, is the primary suspect. But there are more technologies that you're actually going to hear about later in the forum. So we're seeing LEDs making comeback. We're seeing nonlinear polymers making comeback. And, light wave logic, congratulations to Mike, become a NASDAQ-traded company with a valuation more than $1 billion last week. So my message is, don't think it's a solved problem. I think there are many problems that are still looking for solutions. And I encourage you to continue to innovate and continue to bring new technologies to the market. With that, I'll thank you, and I'll take any questions from the audience.
Thank you, Vlad. Any questions for that? Chris?
You showed the various charts where you show silicon photonics portion, then an indium phosphide portion, and maybe a gallium arsenide portion. For instance, in the case of an Intel, when they put indium phosphide onto the silicon photonics, where do you parse that out, or is it all counted together?
Right. So for the sake of people who are watching it online, I'll repeat the question. So the question was, how do we define silicon photonics? Because many devices use a combination of indium phosphide. So for example, Intel products, they put indium phosphide laser chips onto their silicon photonics circuits. So we are making it easy for silicon photonics. So our approach is that if the modulator is silicon photonics, we count it as silicon photonics. But you're absolutely right. They use indium phosphide as well. So the indium phosphide category is only pure indium phosphide. So there's no silicon photonics mixed in, at least not on the transmitter side. So we're looking by modulator technology when we look at the market. Very good question. Thank you.
Nicola Liddens of VI Systems. You mentioned, and it was correct, that actually motivation for silicon photonics is partially related to the problems in reaching high speed of conventional indium phosphide directly modulated lasers and also VCSELs in gallium arsenide-based system. However, I refer to OFC recent and other results. Recently, it appeared that it's easy actually to make 100 gigahertz indium phosphide directly modulated lasers. And it's also for VCSELs, the main problem to measure the bandwidth now is not the VCSEL, but the pin. Because you need to measure 100 gigahertz, you need a 100 gigahertz pin, and for top eliminated multimode pins, it's a problem. So without increasing current density, the bandwidth problem seems to be solved. So basically then the motivation for silicon photonics on the side of modulation is sort of gone. And I refer to talks of NTT, I refer to talks to Broadcom. So how would you comment it? Imagine the bandwidth problem is gone for directly modulated lasers.
Right.
What will happen with silicon photonics?
Well, I completely agree with you, and that's one of the reasons we see indium phosphide and gallium arsenide continue to be used, because yes, they can reach to higher speeds. The arguments in favor of silicon photonics is that reliability may be improved for high-speed silicon photonics modulators because, as I mentioned, lasers tend to degrade faster at higher current densities. I agree with you, it's debatable. The other argument that's probably more clear is that co-packaging with DSPs will be an advantage. So if you can co-package optics with a PAM4 DSP into a single chip and have very short interconnects, I think that'll be an advantage. But the key point I'm making in this presentation, it's not the magic technology that drives adoption of silicon photonics. It's business strategies of companies who enter this market by bringing something new. And they have much bigger goals in mind than competing with gallium arsenide or indium phosphide. For Intel, it's decades from now when they anticipate to see chips requiring optical connectivity in a variety of applications.
So one quick question.
Thank you, Vladimir. My question is that, I can see silicon photonics industry, there must be a big guy or startup or an R&D-based company is divided. So it cannot be a very good ecosystem for market. So I just wonder, you have a good insight about the market for a long time. So do you think those kind of startup, like silicon photonics startup company, they closely working with a legacy style transceiver company to find out new level, not so big, but some kind of middle-sized transceiver, company level. Can it be possible?
I hope so. We see a lot of very smart people starting companies and bringing, fine-tuning silicon photonics capabilities. But I agree with you. Probably the first wave of acquisitions in this space is behind us. But, I think the interest in technology will continue. And as I mentioned, we see more interest from companies like NVIDIA, for example, or AMD. So there may be other big companies that will choose to acquire expertise in this technology. So I think my message is continue to innovate.
Let's thank Vladimir. Great talk.
Thank you.